Hello and welcome to Bedroom Physics. Today I'm going to be talking about multidimensional motion, motion in a circle, and relative velocities. In the last video, we talked about motion in one direction, in the x direction, or the y direction, or the z direction. In this video, I'm going to be combining all of the different directions and making it into a vector. For example, I want to combine not only the motion in the x direction, but my motion in the y direction and the z direction, which will form a vector s. And vector s is a position vector. So, using unit vectors, I have motion in the x direction times I hat, plus motion in the y direction times j hat, plus motion in the z direction times k hat. So the motion in each specific direction is corresponding directly to each unit vector. And this also applies for the velocity and acceleration. For the velocity vector, I would have the velocity in the x direction times I hat, plus the velocity in the y direction times j hat, plus the velocity in the z direction times k hat, and so on with the acceleration. In the last video, we found out how to solve for velocity average, and in this case, it's pretty similar. It's a change in position over the change in time. But instead of the change in position in a specific direction, we have the overall change of position, the change in position of vector s over the change in time. And that would be the velocity vector average. And if we want to find the velocity vector, the instantaneous velocity vector, then we would do ds over dt. And I just wanted to exemplify here. If we take a derivative, by the way, again, ds over dt is the velocity vector. If we did an action to the vector s, then the action would be done to each component individually, not all of them combined. In the vectors concept, we talked about this. We don't combine i's with j's and k's. So if you do an action here, you're going to have to do that action to each individual one. So if I take a time derivative of the position vector, then I'm going to have to take a time derivative of the motion in the x direction, and the time derivative of the motion in the y direction, and a time derivative of motion in the z direction. Now, the main thing about multidimensional motion is that sometimes you're going to be given a velocity or an acceleration that is not only in one direction. You would be given a vector, right? So a magnitude and a direction. If you were given a vector that's not specifically in the x axis or the y axis, then it's going to have a x component and a y component, right? So when we use our kinematics formulas and we want to solve for motion, then we're not going to use the magnitude of the vector v, we're going to use the components of vector v. So if we were solving a kinematics formula in terms of y, then we would use v of y, which is equal to the magnitude of the velocity vector times sine theta. And if you're using kinematics formula or the motion formulas from the last video in terms of x, then our velocity in the x direction would be the magnitude of the velocity vector times cosine theta. An example of this would be if you're looking for v of x final. So v of x final is equal to v of x initial plus acceleration in the x direction times the time. Now, the magnitude of vector v times cosine theta will be substituting for v of x initial. And we would have v of x final is equal to the magnitude of vector v times cosine theta plus the acceleration in the x direction times time. Of course, if the acceleration vector was something similar to this, and it had x and y components, then it would be acceleration, the magnitude of the acceleration vector, times cosine theta times time. Moving right along to motion in a circle. So there's two types of circular motion. There's uniform motion and there's non-uniform motion. For uniform motion, it is when the acceleration is perpendicular to the velocity, while non-uniform motion is when the acceleration vector is not perpendicular to the velocity. The main difference is when the acceleration is only perpendicular to the velocity, the acceleration vector does not have any components that are parallel with the velocity. So the velocity is going to stay constant, and the only thing that's going to change is its direction. So if a point has an acceleration perpendicular to the velocity, it's always going to be turning to the right, but the velocity is always going to be the same. In non-uniform motion, we have a velocity vector that not only has a component straight down or a perpendicular component, but it also has a parallel component. So the velocity is going to be affected by this because it has an acceleration in the same direction. In this case, the velocity will be increasing. It's also important to note that acceleration perpendicular to the velocity vector is known as radial acceleration or centripetal acceleration. Centripetal means seeking the center, and the acceleration parallel to the velocity vector is tangent to the velocity vector. In this case, the acceleration vector is going down and backwards, which means the acceleration, the parallel component acceleration, is going to be decelerating, which means that this velocity is going to be decreasing as opposed to this one, which is increasing. And of course, we still have our perpendicular component, our radial acceleration, down here. But let's go back to talking about uniform acceleration. How do we solve for the radial acceleration? Well, let's make a model, okay? So when there's a displacement, in this case, a point is going from A to B in a circle. So we have a change in arc length. This is no longer S for position. It is a change in position, but this is S for the arc length. When there's a change in arc length, we have a change in theta, but we don't have a change in the radius, okay? But keep in mind that the acceleration vectors, since this is uniform and the acceleration vector is always perpendicular to the velocity, the acceleration vectors are going to line up with the measurements of the radius, as you can see here, which means that the velocities are going to be perpendicular to the measurements of the radius. So since the velocities are perpendicular at each point, then the angle between velocity A and velocity B is going to be the same angle as the change in the arc length here, okay? And since this is uniform and the velocities are constant, then V of A is going to be equal to V of B. And since the radii here are equal to each other, you're going to have a triangle that's exactly similar. And while they might not be exactly the same, the ratios are going to be the same, which is going to lead us to make an equality. We're going to have the change in velocity here that we've made from our triangle. And remember, from vector addition, we have V of A plus change in V, and it's going to equal to V of B. Of course, V of B is equal to V of A. But we have a change in V over the magnitude of change in V over the speed, and it's equal to the change in arc length over the radius. And if we just move V over, we'll have the change in V, the magnitude of change in V, and it's equal to the change in arc length times the speed over the radius. But we know that the change in velocity over a change in time is equal to the acceleration. So if we divided this formula by a change in time, we would get the acceleration average. But more importantly, we're going to get speed over the radius times change in arc length times change in time. And remember that whenever we have a change in distance over a change in time, then we have a velocity. So this right here is going to be equal to a velocity average. But when we take the instantaneous acceleration and we take the limit of the change in arc length over the change in time as time gets infinitely small, we're going to see that this velocity is going to approach exactly the speed from the velocities here. And so we're going to end up with an acceleration radial, or the radial acceleration, the centripetal acceleration, the perpendicular acceleration, that is equal to the velocity squared over the radius. Another important thing about motion in a circle is that we start looking at periods. So a period is the amount of time the point takes to travel a full rotation of the circle. How would we solve for that, right? So we have velocity, which is the distance over time. So if we knew the distance that it traveled, we could find out how much time it would take. Remember, from unit manipulations, all we do is flip meters per second to seconds over meters and multiply it by meters. So we're going to have 2 pi r, which is the perimeter of the circle, over the velocity, so over a distance, so distance is going to cancel out, and the time is going to come up. And so our period is going to be in seconds. And of course, in the infinite wisdom of physicists, we have t for period. But more importantly is that we can solve for the velocity using this formula. If we move 2 pi r over on top of the period, then we're going to get velocity. But we know that the radial acceleration is equal to velocity squared over r. So we can plug this formula into the acceleration formula, and it's going to be equal to 4 pi squared r over the period squared. Now it is important to remember, however, that it's the period that's dependent on the velocity. So when you're doing non-uniform motion, where the velocity is not constant, where the velocity is changing, then you're going to have to find the velocity at the point that you're looking at in order to find the period at that time. And so in order to find the acceleration using this formula, you would have to solve not only for the velocity at a given time, but also the period, and then back to this formula. In my opinion, if you've already solved for the velocity at a given point when you're doing a problem where it involves non-uniform circular motion, then just use this formula, because then you only have to deal with the velocity and the radius. Now the last thing that I want to talk about is the relative velocities and relative changes in distance. So say I get in the car and I turn it on and I go driving and I'm sitting down in my car. Relative to my car, I'm not moving. But relative to someone who's parked and watching me drive, I'm moving at the velocity of my car. So consider an example where there's a passenger in a bus and the bus is moving and the passenger is moving within the bus and there's an observer watching the passenger. What's the velocity of the passenger relative to the observer? Well, first we have to solve for the velocity of the bus relative to the observer, right? So we have a bus and let's say it's moving 5 meters per second. So relative to the observer, you and the bus are moving 5 meters per second. And then we have to solve for the velocity that the passenger is moving within the bus relative to the bus, because the person is already moving the velocity of the bus. When the passenger moves within the bus, then it's going to be an additional speed or a subtraction of speed. If the person is moving to the back of the bus, it would decrease the velocity. If it was moving to the front of the bus, then it would increase the velocity. And so the velocity of the passenger relative to the observer would be the velocity that the bus is moving relative to the observer plus the velocity that the passenger is moving relative to the bus. Or in other words, v of the passenger relative to the observer is equal to v of the passenger relative to the bus plus the v of the bus relative to the observer. In any case, this has been the concept video for multidimensional motion and circular motion and relative velocities. I hope to see you in the example video.